Hi, this is John Moore with JHM Technologies. Here today we're going to talk about designing for close molding, whether that be RTM, light RTM, high pressure RTM, even vartm. We all have the same concerns for these processes regardless of the acronym or the method that we're actually going to be molding. We're talking here about the part design. So the first thing is that we can't have any die locks. Now, what is a die lock? Well, an example of a die lock part would be this air duct. You can see this duct is in this area here, but it's also got this channel. If we were to mold it in this plane, in other words, if we were to parting line here on the mold, the lower half here, the upper half, this area would be locked. The mold wouldn't be able to be opened. So this actual part, the way it was made, was we put it in this position here so that the line of draw is in this direction. So we're able to have a male mold with the channel down below and this channel area here, but when the mold opened up and the part came out, it wasn't locked into the mold. So that's critical when it's in a closed mold. Now here we're talking RTM, light RTM, high pressure RTM. We have two mold halves. Technically, in a vartm process where we had a silicone bag or a nylon bag, we'd be able to mold this against a tool surface and then pop it off. But specifically for this discussion, let's consider two rigid mold halves. So in that case, here's a similar part that has no die locks. Now in that, we're able to have a male tool that would be the shape as you see on the outside, and a female tool. We can load it with fiber covering all areas, close the mold, and then open it straight up with no die locking concerns. So that's critical in our part design. The next is we have to have positive draft. And I'm saying greater than 1.5 degrees is preferred. So here it's obvious we've got more than enough draft. These vertical walls are close. They actually have 1.5 degrees. But by having that positive draft, we're able to open and close the mold and demold the part easily. If we had no draft, the mold would drag as we're opening, and the part would drag on the mold surface. So positive draft is another element. Uniform thickness. Now in that case, you take this part for an example. You can see the red is highlighted the edge of part. Now, that part is uniform in all the radiuses and across all areas. That's ideal. If we end up with thicker radiuses, or by our design intent, we make thicker areas of the part. Well, first let's talk about the radiuses. If those radiuses are thickened and they have the same amount of fiber as they do in the nominal area, you will tend to trap air and have porosity throughout the part, but specifically air in the radiuses. So to have a consistent thickness is critical to the part design. Next, if we decide that we want thicker areas for strength, that can be done, but what we're going to end up having to do is put extra fiber. So we want to think about the operator and their technique. They'll have to put in extra pieces of glass strategically where the thickened area is. We have to keep uniformity in our glass to resin ratio. So in thicker areas we need more glass, thinner areas we would have lower glass content. The other element though, if we need thicker areas, we can use cores. Here's an example using wood as a core. This is a cutaway of a seat to a boat. So we have uniform thickness, we have uniform thicknesses around the core, and in this case they're used wood. It could be foam, it could be a variety of different materials that we use for the core, but nevertheless, we're able to have fiber and resin follow around the core with the core in the center for strength. So if we consider those values in our design, we'll have a uniform, strong part that's easy to load and easy to repeat in the process.